Good morning, and I'm Mert. I'll be giving you a presentation about LLK grammars, RRK grammars, and their relationship. So, what is a grammar? Grammar refers to a formal system that defines how strings in a language are constructed. It plays a crucial role in determining the syntactic correctness of a language and forms the foundation of parsing and interpreting languages and other formal systems. So, LLK grammars. The term LLK refers to a specific class of context-free grammars and deterministic top-down parsers that processes them. The first style refers to the left-to-right scanning, reading the input starting from the left, and the second style refers to the leftmost derivation. The parser constructs the parse tree starting from the left-hand side. The term K is the look-ahead amount. The parser can peek at the next K symbols starting from the left in order to predict about the future. LLK parsers are predictive parsers. They try to guess which prediction rule to use before it actually sees the entire content of the rule. Think of it like this. You are at the fork in the road, a non-terminal with multiple rules which checks K number of steps in the future. So if your K is 1, you only look at the next symbol in order to predict the path you are supposed to take. If K is 2, you look at the next two symbols, and in 3, you look at the 3 symbols, etc., etc., etc. The parser K equals 1 is the most common because it keeps the parsing tables small and efficient. And for their construction, LLK grammars must follow these two rules. First of which is no left recursion in order to prevent infinite loops within the grammar, and no ambiguity such that for any non-terminal and any K-lookahead symbols, there must be exactly one production rule that could match the intended string. For their implementation, LLK grammars map directly to two types: recursive descent, which means that we write one function for every non-terminal in our grammar, and table-driven, in which we use a table and a 2D separate lookup table. Now, for the RRK case, RRK stands for right to left reductive grammars, which are a class of context-free grammars. They use a bottom-up parsing strategy that seeks to determine which production rule to apply by looking at the right-hand side of the current string. It can be observed in three main topics. First of is directionality, right to left scan. The RR parser consumes the input in stream in the reverse order, so it scans from right to left. It naturally encounters the rightmost parts of the structure first, and it identifies the handle string at the end of the input. This proves that the orientation of a language does not matter mathematically. If a machine can parse a language reading format, a symmetrical machine can parse the reverse language in reverse. It is above the basis of the mirror theorem, by the way, and I will get to it a little bit later. The second is power. In formal languages, theory of power refers to the specific class of languages a grammar can define. Equivalently, the set of languages that can be parsed by an RRK parser is identical to the set parsed by an LRK parser. They both cover the entire set of deterministic context-free languages. Although they have the same power, they require different data parsing. One starts from the left and the other one starts from the right. On the other hand, LLK is a less powerful structure. It's a context-free top-down parsing. And finally, for the reduction part, a bottom-up build, RRK parser starts from the leaves of the code and tries to reduce them back to the start. It uses a tail strategy in which the RR parser looks at the tail of the sequence to make decisions. It tries to find a matching pattern at the end of the buffer, and once it matches a rule, it pops the result of the stack and pushes the non-terminal. It repeats this until only this starting symbol remains. Now for the mirror theorem. The mirror theorem is the formal mathematical bridge that explains why RRK and LLK are mirrored versions of each other. The formal definition goes like this: a context-free grammar is LLK if and only if the reverse grammar is RRK. The core of this theorem lies in when the parser makes a decision. For the both sides of this case, I will explain it. LLK, the decision factor goes as follows. An LL parser stands at the start of the rule. It looks at the first case signals to the right to decide which production to expand. And for the RRK case, an RR parser stands at the end of the rule and it looks at the last case symbols to its left to decide which production rule to expand. Because this decision-making logic is identical, but just reformed a bit in a different direction, if you reverse every string in an LL parser, you get a valid RR derivation. The prediction steps of LL becomes the reduction steps of the RR. This theorem holds because conflicts are also inverted perfectly, such that in LL case, if two rules that start with the same case symbols, the parser crashes, and if two rules end with the same case symbols in the RR case, the parser also crashes. So reversing the first string to the last and last to the first, the conflict that result is mathematically identical. Intersection and incomparability. In formal languages, comparability refers to whether one class of grammars can handle all the language of another, while intersection refers to the languages that can be parsed by both. Because RRK and LLK are mirrors of each other, their relation is a mix of structural symmetry and linguistic divergence. In mathematical terms, the RRK and LLK generated languages are incomparable. This means that there are languages in LLK but not necessarily in RRK, and vice versa. It comes down to where the determinism is located. To be an LL language, the language must be deterministic from the prefix, and to be RR, it must be deterministic from the suffix. For example, the language described by the first equation, an allowed parser sees the first character to be B or C and knows exactly which path to take. However, an RR parser scanning from right to left sees an A and it will not be able to immediately decide for lookahead number K less than N. For the other case, as can be seen in the language defined by equation 2, it is RRK and not LLK, since L is equal, L can be deciphered by an RRK in the start, but not necessarily by the LLK for K less than N. For their intersection, a language can be described by both LLK and RRK. If you look at the third language described, you can see that both LLK and RRK can decipher the language without any further complications. Thank you for being part of this presentation. Goodbye.